Welcome back, guys. So today is the follow-up to my previous lesson on Hooke's law. So we're going to look at the relationship again between force and the extension of a spring, how that can be represented on a graph, and then the questions they ask around that. Okay, so make sure you have paper, pen, and your calculator ready to take notes. So before we get into the question we have here, question 5, let's recap some basics about Hooke's law. So a good point to start would be actually the very first question. So what is Hooke's law? So Hooke's law states that the extension of a object, which is usually a spring or an elastic band, is directly proportional to the load applied. Okay, so the extension of a spring is directly proportional to the load applied. So whatever load you add on, so if you double the load, for example, from say 10 newtons to 20 newtons, the spring will stretch by a constant amount. So the spring may start at say 2 millimeter and then change to 4 millimeter, or maybe it starts at 5 millimeter and changes to 10. It's directly proportional. However, there is a caveat to that. This only applies to the object, in this case the spring, up to its elastic limit, right? Which is also known as the limit of proportionality. So the extension of a spring is directly proportional to the load applied, comma, up to the elastic limit. Now, what is the elastic limit? Well, the way I like to think of it is it's the point of no return. So say you take a spring or elastic band or even a paper clip and you stretch it too much and it doesn't go back to its original size once you've removed that force. Well, what you've done there, you've gone beyond the point of no return. You've damaged the material and it doesn't go back to its original size. In other words, you have gone past what is called the elastic limit, how much it can take before it becomes permanently deformed, permanently damaged. Okay. So what does that look like on a graph? Well, we're going to see this in a moment, but let's scroll up. So figure 1.1 shows a graph of stretching force F acting on a spring against the extension X. State the feature of the graph that shows the spring obeys Hooke's law, where you can see very clearly that as the force is doubled, so say from 50 to 100 newtons, so remember weight is in newtons, mass is in kilograms. To turn from mass into weight, you times it by the force of gravity, which is 9.8 newtons per kilogram, sometimes rounded to 10. So we've doubled the weight from 50 to 100, and you can see, right, the extension of the spring has gone from 20 up to 40. So the feature of the graph that shows that it obeys Hooke's law is that the gradient is constant. So sometimes referred to as being it's linear. And because of that, you can clearly see that it's directly proportional. Okay, so the gradient is constant, supporting the fact that it's directly proportional. Right, so we can express this definition and this graph as a mathematical relationship. So I'm just going to, this is not asked in the question, but I'm just going to write it here for your understanding. So F is directly proportional to X. So that little symbol there, that's the proportionality symbol. Okay, and if we turn that into a regular equation, that will become F equals Kx, where K is the spring constant. So that is unique to the spring. So a stiffer spring will have a different spring constant than a spring which is more stretchy. Okay, right, usually X, the extension, is quoted when you use it with force, which is always in newtons, distance is usually in meters. But for most of these questions, you are going to see stretching of springs where the measurement is in millimeters or centimeters, and that's okay. It just means when you are working out the spring constant, so if I rearrange the equation, K equals F over X, it's really important you define the unit of the spring constant. So in this case, my unit for the spring constant would come out as newtons per millimeter. Right, so let's take a look at the next bit. So you can see the next part is this, where we've got to work out K. So, and you can see it's 3 marks. So just chop the top bit of the question there, just so we can, just for simplicity. So it just said determine the value of K. So if we go back to our graph, I have just written this expression here in red, and in order to get the value of K, we can just use the graph to help us. So K is essentially the gradient, and the gradient is rise over run, or F divided by X. So I'm just going to use this point here. So I can use this triangle there. So it'll be 100 is the value of F divided by 40, which is the value of the extension. And that gives me a value of 2.5 newtons per millimeter. Okay. Right, so that is the value of K. So the 3 marks are 1 for the calculation, 1 for showing your correct answer, and then the third one is always for the units. Okay, so it's 2.5 newtons per millimeter. Right, the limit of proportionality of the spring is reached at an extension of 50. Continue the graph to suggest how the spring behaves when the stretching force is increased to values above 125. So that means once you go past 50, which is this point here, the spring becomes permanently deformed. So think about this carefully. That means you add a little bit more force and it stretches wildly. So you get a big extension from not much force. So if that limit of proportionality wasn't reached, the graph would just continue upwards. Let me just show you. Would just continue upwards as sort of this dotted line there, right? But that doesn't happen because at this point it becomes permanently deformed. So if I do this next bit in blue, what happens is you see the graph curve this way. And the reason why is because after this point, just a small amount of force causes quite a significant increase in the extension. Okay, so the blue line, that one there that I've just done, so that will be the answer to this one. Okay, right, finally, another spring has a smaller value of K. This spring obeys Hooke's law for extensions up to 80 millimeter. In fact, I'll do this one in green. Right, up to 80 millimeter. On the grid on figure 1.1, draw a possible line of the variation of F with X for this spring. So it's telling us that the value of K for this spring is smaller. In other words, it has a smaller gradient. So, and it obeys Hooke's law up to 80 millimeter. So therefore, what is this line going to look like? Well, the gradient has to be less than this. How do I know this? Because I've just been told. And it will be a straight line up to 80. So therefore, this new line is going to run underneath the existing one, and you can put it anywhere you like, providing it's a dead straight line. So just going to draw this in with my ruler, and it's sort of going to look kind of like, well, actually do it freehand, but you should use a ruler. It's going to look something like that. Okay, so it's important that you use a ruler for that, just in that freehand. But the gradient is going to be shallower. It's going to be smaller because the spring constant is smaller. What I'd like you to do now is go and check out the other video on Hooke's law I've made, which is more mathematical than this question, and I would say slightly harder. And then once you've seen that, hopefully you'll have a really good idea then of how to do these Hooke law questions in an exam situation.